Here we have yet another Atwoods machine. Alright, looks pretty standard, except this time we do not have a massless pulley. Okay, we have a mass and a radius for our pulley. Now, just a reminder, an Atwoods machine is a pulley with a rope over it and two different masses on either side of the rope, and it will accelerate in one direction or another, and we can determine that acceleration as well as the tension in the rope. Now, in this case, we have a pulley with mass. We're going to say that the rope does not slip. It rolls right along with the pulley nicely, and we want to find both the acceleration and the rope's tensions. Alright, so we'll get started with free body diagrams as usual. We've got M1. I'm going to say that is the positive, the direction that it goes is the positive x direction. By the looks of it, I'd say that is the direction that the system's going to accelerate. So I'm going to define my axes on the picture like this. Alright, that means down is positive for M1, but for M2, the up is the positive x direction. Okay, so doing their forces, we've got M1G, we've got tension attached to M1, and then we've got M2G, tension attached to M2. Now, I do not know that the two tensions are going to be the same because this pulley is not massless. In the past, we had pulleys change direction of tension but never change its magnitude. Well, those were massless pulleys. This pulley has mass and it is able to change the tension of the rope. So we don't know that T1 will be equal to T2 in this case. Alright, now I'm also going to need a free body diagram for the pulley itself. Now this is going to be a rotational free body diagram. This is the positive direction of rotation as matching the positive x directions of the other masses. Okay, so now we need our Newton's equations. Move this over here. For M1, we have the sum of the forces in the x direction is equal to M1 times acceleration in the x direction, and that will be equal to M1G minus T1. Over here for M2, we have the sum of the forces in the x direction equals M2 times acceleration in the x direction, and that will equal to T2 minus M2G. If we observe the coordinate system, we can figure out what's plus and what's minus there. So one thing we should probably note is that the acceleration of M1, the magnitude of M1's acceleration, will be the same as the magnitude of M2's acceleration. Now, we said the tensions can be different, but they still are connected together by a rope. So as one falls, the other must rise at the same rate and the same acceleration. So the two axes here will be the same. Alright, now the equation for my pulley free body diagram. Moving back over here. So if you recall, for a free body diagram of a angular system, we write that the sum of the torques is going to be equal to I alpha, all right, which will be equal to, well, let's see, I've got T1 pulling it that way and T2 pulling it this way. So the sum of the forces equals I alpha, which will be equal to, so the sum of the torques does equal I alpha, but also literally equals the sum of the torques. So we have the radius here and here making right angles with these forces. My positive torque is going to be T1R, and negative is going to be minus T2R. Alright, so one more thing is that wasn't given. We do know the mass of the pulley If we assume that the pulley is just a uniform disk, then our equation for I will be equal to 1/2 mass m3 r squared. Okay, so we also have alpha in the above equation there. Now alpha, that's angular acceleration, and if you think about it, well, as m1, for example, accelerates down, the pulley has to rotate to complement that. So the angular acceleration of my pulley is going to have to equal the linear acceleration of m1 of the rope divided by its radius, right? Any given point on this pulley is going to be accelerating at a linear acceleration of ax. And so to find the angular acceleration, we simply divide by the radius. All right, so let's plug the I and the alpha in here. So I'm getting 1/2 m3 r squared for I times ax over r for alpha is going to be equal to t1r minus t2r. So I see that I have r squared over here divided by r. That gets rid of 1. And then I see I have an r everywhere still, so I can divide through the entire equation by r. And my radius is actually completely gone here. I get 1/2 m3 ax is equal to t1 minus t2. Okay, so that is the result of the free body diagram equation for my pulley, and up here I have the results for the two masses. So let's see if those three can give me my answer. I don't know ax, and I don't know t1, don't know t2, ax, t1, and t2. So it looks like I have 3 equations and 3 unknowns. This should be solvable. Now, if you try to use substitution in this, you may get to the end before you decide to kill yourself, or you may not. So let's use the method of addition instead. It's going to be much simpler. So 1/2 m3 ax equals t1 minus t2. And we're going to add the equation from one of the equations from the top of the screen there, m1ax equals m1g minus t1, and we're also going to add the other equation from up there, m2ax equals t2 minus m2g. So see what happens when I add these. I have a positive t1 plus a negative t1, a negative t2 plus a positive t2, they're all gone, and I'm left with ax, a whole bunch of max's over here. I'm going to pull the ax out as I add, and I get 1/2 m3 plus m2 plus 1 is equal to m1g minus m2g. Alright, so I just added up everything on either side of the equal sign, and I went ahead and pulled ax out of all 3 m terms here. Now, to solve for ax, I'll just divide over, and I'll pull g out of these terms too while I'm at it. So ax is equal to, well, we have got g m1 minus m2 over 1/2 m3 plus m2 plus m1. Okay, so here we have the acceleration in the end is going to be a piece of the gravity, and the piece is in the form of a difference of the masses over the sum of the masses. Like I keep saying in the other Atwoods Machine videos, this happens. You've got a difference of masses over the sum of the masses. Okay, and now to solve for t1 and t2, well, we've got an equation up here that relates t1 to a and t2 to a, so I'll leave it to you to go ahead and plug in our expression for acceleration into either of those above equations, and you can find t1 and t2, and their equations aren't as nice looking. I like this one. Alright, thanks for watching, and that's it.